Hello and welcome. I hope you are having a great day. In this video, we are going to understand about joint, marginal and conditional probability distributions. Let's set up the agenda. So as you can see, I hope the screen is visible. Today we'll discuss about joint probability distribution and we'll discuss about the CDF, PMF, PDF. So this will be for the discrete case. This is for the continuous case. We know all this from the previous classes. So we'll discuss the CDF, PMF and PDF for joint probability distribution, marginal distribution. I'll skip the word probability. So that's implicit. If I say joint probability distribution or joint distribution, they mean the same. Then marginal distribution and then conditional distribution. And within conditional distribution, once we have discussed this, we'll discuss about conditional expectation and conditional variance also. So let's start. First thing, joint distribution. So let me write it down. So what is joint distribution? So till now, whatever we have learned in all these videos, in the previous videos, right? Those were with respect to one random variable. But in real world problems, we have two or more random variables for modeling any problem in a real world situation. So how do we model when we have more than two or more than two random variables? So how do we model those? So for that, this class is there. So we'll understand about how we model two or more random variables. So what's joint distribution or joint probability distribution? This is the probability of two or more random variables occurring simultaneously. Okay, so this is the probability. This describes this value, whatever this function is there, right? So it describes the probability of two or more random variables. RV is a random variable occurring together or simultaneously. Okay, this is what it gives me. And the two random variables can come from totally different distributions. Even one can be discrete and the other can be continuous. Okay, and it will give me the joint distribution of the two random variables put together. That's what joint distribution means, that when we have that value of two random variables, what will be the combined probability of both of them occurring simultaneously. So let me write down. It is applicable. Two random variable may not come from same distribution, same or similar distribution. Even I'll be more lenient. I'll write similar distribution. And for example, one RV can be discrete and second RV can be continuous also. Even that is the case. So this is the case, even that is possible. That's what I'm saying. But when we discuss, we'll be discussing about two similar kind of random variables, similar distributions, discrete and continuous. But this is also possible. I wanted you to know this. So let's so for example, in real world, I'll give you a real world simple example and then we'll see a concrete example. So a real world simple example is, for example, if you have two random variables such as height of a person and the weight of a person. So if you want to see what is the joint distribution or combined probability of a specific height and specific weight, then we say that that this is a joint distribution of height and weight. For example, if we have a person, okay, of height 170 centimeter, and we want to find the weight of that person. So what we will do is that we'll take the weight of all the people who have 170 centimeter height, and the average of that will give me the weight for the 170 centimeter person height. Okay, So these examples will keep on coming later also. I'll discuss about these examples again. But there will be one common example which will be running through, which we'll use throughout the this lecture to understand all the three concepts. Okay. So let me give you. So one example that I gave you, right? So what was the example that, for example, I'll write it down for you. For example, two random variables can be like, for example, one can be height of a person x and weight of a person y. Say for example, we can model the problem anyway. Height can be Gaussian distribution, and weights I can keep as discrete or Gaussian, whatever way. But there are two random variables. If I want to have the joint distribution, tell us the probability of person of a specific height and weight, that combination. So for example, if I want to find a weight of a combination of a person, say 170 centimeter height and 70 kg weight. So I want this combination. What is the probability of finding a person of this? This will come from my joint distribution. Okay, I hope this is clear. So let me set up the example which will be more clear. So for example, let's say we have two bags, okay, and both of the bags contain, the first bag contains 2 red balls and 3 blue balls, and the second bag that contains 3 red balls and 2 blue balls. Okay, so how is it? So there are 2 bags, one bag, second bag. So this is your, say for example, this is bag 1, this is your bag 2, and what do they have? So there are how many red balls in the first one? First one has, say for example, 2 red balls. And the second one has 3 red balls, 1, 2 and 3. And the first one has, say for example, 3 blue balls, and this has only 2 blue balls. Okay, this is my setup. And so we will model the random variables as, so this will be, if I choose let me make it thinner. If I choose a ball from bag 1, I will model it using the random variable A, and if I choose from bag 2, I'll model it using the random variable B. So these will be my random variables. Okay, so now, so what is the question? So there are 2 bags, bag 1, bag 2. Okay, and now my statement is that a ball is randomly selected from each bag, from bag 1 and then bag 2. Okay, and both the draws are independent of each other. Okay, a ball is randomly drawn from each bag. Okay, such that both draws are independent. That is the case, right? That will be, so I'm just being more explicit, independent of each other. So we have this case, so both the draws are independent of each other, and then whatever I have mentioned here, right? So let me write that. So let A and B be the discrete random variable. So let A and B be discrete random variable associated with outcome of the draw from first and second bag respectively, of the outcome of the draw, which color ball is drawn from the first bag, draw from first and second bag respectively. So whatever I have drawn here, I have written these in words. So bag 1 contains 5 balls, bag 2 also contains 5 balls. One has 2 red balls. First one has 2 red balls, 3 blue balls, 3 red balls, 2 blue balls. So if I draw a ball from bag 1, so that is modeled using random variable A, and if I draw a ball from bag 2, I'm using a discrete random variable, B for drawing the for modeling the problem. So let's see what will be the probable solutions. So let's draw this out. So this will be simple. So let me draw. So either it can be, so let me draw this way first. Okay. So either A can have a red ball or B can have red ball, and then B can have a blue ball or A can have a blue ball. So there are two draws, right? So this is two draws. First draw is for A and the second draw is for B. So either the first one has a red ball and the second also has a red ball. First has a blue and the second has blue, and all the four combinations: red, 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 blue, red, blue, blue, blue. So these are four combinations, and let's write down the probability of each of them. So what will be the probability of? So let's focus here. So I have to write, so both the variables are independent. So what will be the probability of what will come in this column? Sorry. So this is this is my setup. So I have drawn this. So this gives me all the four combinations in the tabular format. So what will be the probability that I'll get here? That the probability of drawing a red ball in the first draw and a red ball in the second draw. This is what this cell will give me, right? So this will give me the joint probability of a red ball in the first draw and a red ball in the second draw. This is a joint probability. Each cell will give me the joint probability of that combination. So what is the probability here? So let's write it down. So let me write it down using this color. Okay. So this can be, what will be the probability of drawing a red ball in the first draw? So this is coming from the first bag. That will be 2 out of 5. So this will be 2 by 5 into, both are independent. So the joint probability will be multiplication of both. And what will be the probability of drawing a red ball from this bag too? There are 3 red balls out of 5. So this will be 3 by 5. So what is the total probability? 6 by 25. And this is nothing but our joint probability. Okay. Similarly, all the combinations will have the joint probability: a red ball and a blue ball in the first and red ball in the second, and blue ball in the first and blue ball in the second. All these columns, all these cells, each cell, there are 4 cells, right? So let me make this also here. All these 4 cells will give me the 4 probability distributions. I hope that is clear. And this each cell value is the joint distribution. Okay, so let's quickly fill this up so that you know. So let's calculate all the 4 probability distributions, and then I'll give you the property also. So now quickly, what is the distribution here? Getting a blue in the first draw, that is 3 by 5, and getting a red in the second draw is 3 by 5, is equal to 9 by 25. Okay. Then getting a red in the first draw is 2 by 5 into getting a blue in the second draw is 2 by 5. That is equal to 4 by 25. Okay. And then let's say from here. So now we have blue in first draw. So that is again 3 by 5. 3 by 5 into a blue in the second draw. So here it will be 2 by 5. So this is equal to 3 to the 6 by 25. So these 4 values are my joint distributions: 6 by 25, 9 by 25, 4 by 25, 6 by 25. And there's an important thing: if you sum up Okay, sum up all these distribution, all these joint distributions, right? They should sum up to 1. That's the required property. It should sum up to 1, and let's see if it sums up to 1 or not. So the combined total joint probability is equal to 6 by 25 plus 9 by 25 plus 4 by 25 plus 6 by 25. Let's see. 6 plus 9, 15 plus 4, 9, 19 plus 6, 25. This is equal to 25 by 25. This is equal to 1. So this satisfies. So hence this is holds the property for a joint distribution, that all of it should sum up to 1. I hope joint distribution is clear. So let me formulate it, right? Give you some formula so that you remember. Okay. Now, so again we'll define the CDF, PMF and PDF. Okay. So what will be the CDF? Joint CDF. Joint CDF. What will be the formula? How do we give this? So joint CDF is given by, how is the formula? X comma y. This means X and Y. Okay. The CDF of X and Y. So if I have variables, there are some books which gives A and B. I'll make you familiar with these notations. They use X, Y, A, B. So I'll give you A, B notation also. And then later on I'll use X, Y notation itself. Okay. So I'm just making you familiar with the different notations so that you don't get confused when you see these notations. Okay. What is this? Probability of X less than or equal to A, and when we comma is read as and. Wherever you see comma, read it as and. Okay. And y is less than or equal to B. Okay. Where minus infinity, A and B lie between minus infinity and plus infinity. So this is your joint CDF. And what will be the for the discrete case? For the discrete case, what will be the value be? Same thing. How will we write it? F of X comma Y, X and Y, A and B. I'm using this A and B now, and later on I'll use X and Y. I'll come back to the X and Y notation. It's just to make you familiar. Only here I'll use it. So again, this will be probability of X. I'll write it so many times so that you remember it. So this is what it is. Probability of all the values. This is cumulative, right? Remember CDF, this is cumulative distribution function. Is summation, a running sum of all the probabilities till A, of all the values of X till A. So we sum it up, and Y will be less than or equal to B. What will be the value? How we write? So Xi less than or equal to A, and summation Yj, I will write it as, I'll use another variable, Yj less than or equal to B, and then we do probability of X is equal to Xi, comma Y is equal to Yj. Okay. So this will sum up for all the values less than or equal to A. So Xi will run from whatever values A can miss, X can take from minus infinity till A. Okay. So what will be the continuous case? Similarly, so here if you see the joint probability is again the summation of both of them. This is a product of this and this, comma is read as and, probability of this and this, that is the joint probability. What is the continuous case? So just make you familiar with the terminologies. Capital F is used for the CDF. I hope you remember that from the CDF field. A comma B is equal to, again I'll write the notation, less than or equal to A, Y less than or equal to B. This is equal to, what will be? This is summation. Here you use probability P, and for PDF density function, this is for discrete case, right? So for this continuous case, this will be written as minus infinity to A, minus infinity to B less than or equal to, and then F of X comma Y, small f. Okay, and we integrate for both dy and dx. So this small f is for the, this will denote, this denotes my PDF, this is my PMF. Okay, so for again, so there is one more thing, let me write it down. So the properties, here, so this is also called, this is the, so let me write it down in the PMF form only. So let it be here, let it go back. So let me write down as a joint PMF. So again, let's write down the joint PMF itself. This is for the discrete case. What will be the joint PMF? Write it again for the discrete case, countable case, discrete case. The formula will be probability of x comma y is equal to probability of x is equal to x. Okay, so PMF is at a particular point, CDF is the cumulative, this is the running sum, it is the sum of all the values. PMF is at a particular point because we have these points, right? Remember that. So x equal to x and y is equal to y. This is equal to probability of x is equal to x comma y is equal to y. And do you remember the properties that it should hold? So what are the properties? It should be, so given that, such that probability of x is equal to x comma y is equal to y, that both the conditions hold, is greater than or equal to 0 for all pairs of x comma y. And the second condition is all of the probabilities should be positive, that's the property of the probability itself, and the sum of all the probabilities should sum up to 1. So what will be the summation? Sigma I, sigma j, and then probability of x is equal to xi comma y is equal to yj. This should sum up to 1 because the max total probability is 1. All these should add up to 1. So I hope joint PMF is clear. So this is notation, and this is what the example that we discussed here, right? So this is a discrete case only. Okay, so let me write down the joint PDF also. Let's come down. So it will be the let me use the black one. What will be the joint PDF? With the joint PDF. So this is for the continuous case. Let me write that down. And continuous case. And here the donation. How do we donate this? Denote f of x y, x comma y for x comma y. This is my PDF. Okay. And generally this is equal to, like, we give a, okay, simple form, f of x comma y, x comma y, dy dx. So this x belongs to 2 dimensions. This notations and all you will declare. This means that r of 2 dimensions. Okay, that is x and y dimension. This is for the real number of 2 dimensions. This 2 means that, and r simple means this is 1 dimension, and r of n means n dimensions. R of d, we will come a lot around that. So when I discuss about the vector algebra, then I will discuss in detail about this. Okay, but generally there is a quick thing that this joint distribution maps from 2 dimensions to 1 dimension. Okay, just good to know. Don't worry, you'll get familiar with these notations later. Okay, and there's one more thing about PMF. What is the PMF? It is the derivative of the CDF, cumulative distribution function. So we'll write that in that way also. F of x comma y, xy, this is equal to the second. So we'll differentiate it with respect to both y and x. Okay, and what we'll differentiate the CDF. This is my CDF and this is my PDF. And if you don't understand these notations, so we'll discuss this during the calculus. This is partial derivative with respect to y and then partial derivative with respect to x. So once we differentiate this CDF with respect to y, keeping x as constant, and then we differentiate this function CDF with respect to x, keeping y as constant. So this is called partial derivatives, when one variable is counted and the second one remains constant. Okay, so I'll put those links, all the calculus video links, in the description. So I hope this joint probability is clear. So even these will have the properties. So let's me write the properties, similar properties. What will be the properties for this? All these properties are coming from the past itself. So I'm just revising it so that you remember. So the first property would be same thing, that probability for any given range, right, for xy is always greater than 0 for all combination of xy, and the summation would be 1. Sum of all the area under the curve of joint PDF would be, joint probability distribution would be 1. So we'll integrate from minus infinity to infinity, minus infinity to infinity, both the variables x and y, and this whole thing should sum up to 1 dy and dx. This should be equal to 1. So I hope the joint probability distribution is clear. Now let's move to the next topic, that is marginal. So I'll move to the next page. So marginal distribution. So what is marginal distribution? So here in this case, so I'll use the same example again. I'll use this same example for all the three. Okay. So earlier we had individual probabilities, and we calculated a joint, the combined probability of both the variables. So I had individual probabilities, I found out, and then I multiplied both to find the joint distribution, probability distributions. And now if I say that you have only the joint probability distributions, and now you want to find the individual probability of one variable. Say for example, if I have this all these are joint distributions for different combinations of A and B, red and blue, being drawn in different terms. So if I have got only these values, I don't have these things. Okay, if I have only this, so let me rub this off. For example, I have only these values. Only joint probabilities are given to me. And this information is provided. And if I ask you that, now how do we calculate the probability of only this, that a red ball is drawn in the first draw? What is probability that I have drawn a red ball in the first draw? So I have the combined probability, joint probability of both, and now I want to find out what is the probability of only one random variable. We modeled this as two random variables. So given that we have two random variables and we know the joint distribution, I want to find the probability of only one random variable. How do we find that? So the given thing is we have the joint distribution, the value. Okay, that distribution we have. So how do we find that? So the marginal distribution gives me that value. So let me formally write it. So what does this mean? Marginal distribution means that probability distribution of an individual. It gives me, what does it give me? It gives me the probability distribution of an individual random variable in a joint distribution. Okay, that is without considering the outcomes of other variable. Here in this example, so if I have to ask, this is given that in this, if you consider only this, that in the first draw I got a red ball, what is the probability of that? I got these values, okay? So the probability of getting a red ball in the first draw and the red ball in second draw is 6 by 25. And the probability of drawing a red ball in the first draw and a blue ball in the second draw is 4 by 25. Now if I ask you what is the, given this information, I have only this information, what is the probability of getting a red ball in the first draw? You have this information, the information in this cell. How do we do that? So this is simple. So we say that without considering the outcome of a variable. In joint distribution, say for example, we have PA and B, this comma is A. So generally this is PA into PB. And we have this value. Okay, this is some value. Okay, some value is there. We have got this. Now, if I want to find only the probability of A, how do I get it? If I have this value, this is, I know this, sorry, this is known, this is some value, X, say. So if I know this combined value, can I say that PA is equal to some value? This is just for intuition, don't take it literally, okay? X by PB. If I want to find PA, this is what I want to find, the probability of a red in the first draw. So what if, so one way is either we know PB, we don't know that, we know only the joint distribution, we have only the combined value. Okay, we know only this value, but we don't know this. So what if we make this PB is equal to 1? If I make this P of B is equal to 1, then will I get this value, whatever is the value? How do I make this PB is equal to 1? And whatever is the value after that, then that will be there. So it's just for intuition, don't take it literally. So this is what I'm trying to explain, that without considering the outcomes of the other variable. Without considering the outcomes of the other variable means that the other variable doesn't exist. Or even if it exists, the probability of having that is always 1. So if that is there, and if I have the product joint distribution of both of them, if the other one is 1, if I make this 1 somehow, that I consider all the possible outcomes of this variable, then the probability of this will become 1. So whatever value I'll get will be the probability of A. This is what marginal distribution intuitively means, that if I want to find the probability distribution of A, then I sum up the joint distribution over all the possibilities of the other variable, and this will sum up to 1. And because of that, finally what will happen is that whatever value we'll get out of the joint distribution, that will be my marginal distribution of the variable A. I hope that is clear. So let's do this in this example itself. Okay, so here I told you, right? So my given thing is that I know all these values. Now I want to find what is the probability of drawing a red ball in the first draw. So for getting this, I have to make the B as 1. So what are the two possibilities of B? These two. If I sum these two up 1, these two values, so will this become 1 now? So all the probabilities are covered here, of B is covered here. So if I sum this up, will I get the probability of B? So what is the sum here? This is the sum is there. Let me use a different color. For example, this is 6 by 25 plus 4 by 25. This is equal to 10 by 25 or 2 by 5. Can I say this is probability of A? 2 by 5. Let the probability of drawing, okay, what were the balls here? Let me draw it back. So earlier there were 2 red balls here, 3 red balls here, and 3 blue balls here, and 2 blue balls here. So without considering the outcomes of the other variable means summing that up to 1. So if I don't consider what I'm getting in the second draw, does that mean that probability of getting a red ball in the first draw means probability of drawing a red ball from the first bag is 2 by 5? And isn't this what we have got it here? If I sum up these two values, 6 by 25 plus 4 by 25, is this not the same? So this is what it means, that I have got the joint probabilities, I sum it up across all the possible values of the other variable. That's what it means, that I don't consider the other variable. Means that is always present and its probability is 1. And how do I make the probability of the other variable 1? By summing it up across all the probabilities, all the possible outcomes of the other variable. Okay, I hope this is clear. So let me write it down for you. Just a minute. So this here, so let me write it down here also. Then this is here P of A, and here if I draw one more line, then this will be your P of B. Similarly, I can find all the other probabilities also. So what will be the probability of B here now? So getting a red ball in the second draw, sum it up this way. What will be the value? That will be equal to 9 by 25 plus 6 by 25. This is equal to 15 by 25. Okay, so let's check. So getting a red ball in the second draw is equal to 3 by 5. So getting a red ball in the second draw is 3 by 5. Similarly, this is 4 by 25 plus 6 by 25. This is equal to 10 by 25. This is equal to 2 by 5. What does this mean? That probability of getting a blue ball in the second draw, B is for the second draw, right? A and B for outcomes of the first and second draw respectively, second bag respectively. So getting probability of B here in this second case means getting a blue in the second draw. So this is 2 by 5. This is what it's giving, 2 by 5. These all values are the, and similarly let's write down here also what will be the value here. So for example, this will be 9 by 25 from here plus 6 by 25. This is equal to 15 by 25. This is equal to 3 by 5. So what does this mean? That getting a blue ball in the first draw or first bag. So this is your 3 blue balls in the first bag. So all these values, that is sum, we have kept the other one as constant or summed it up across all the possible values. So other probability of the second variable becomes 1. So whatever remains is the first variable only. And these all sections here, these are giving you the, this is your marginal probability of A. Here it is marginal probability of B. With this, I think this should be pretty much clear. What is marginal probability? Now let's move. Let's write down the formula and it will formalize it more clearly. So I'll cover all the scenarios again. So what will be the marginal CDF? How do we denote it? So you're familiar with the notations. So this is, so we know that what is the joint CDF? We know this joint CDF is f of x comma y comma is and this is, again I'll write it as AB1 only. P of x less than equal to A and y less than equal to B. This is what it is. Summation of all the values till A till B. Such that minus infinity is less than AB. So these values lie between minus infinity and plus infinity. Okay. So what will be the marginal CDF from here? CDF is cumulative distribution function. What will be the marginal CDF? This is of CDF. So this will be of X. So now marginal, this was for both of them, X and Y. Sorry. So joint is for both X and Y. Marginal will be for only one variable. So let me write of X. So this will be only f of X. And if I say that, so in this thing, that how will we denote it? So a comma, if I said the other one is infinity, so this is, it will be minus infinity to a. This less than equal to a means all the values less than equal to from minus. So if I give it minus infinity, this starts from minus infinity to a. So if I give it infinity for b, it gives minus infinity to infinity. Does this not cover all the range, all the possible values of y? Means whatever is the probability here, this will sum up to 1. It will give all the possible values of y. So we write that as infinity, that it will give me all the possible values of y from minus infinity to infinity. That's how make the other one as other variable as 1. We don't consider that. So this will be equal to probability of x less than or equal to a and y less than infinity, means all the possible outcomes, covers all possible outcomes, whatever is there of y, it will give, and it will sum up to 1 because all the values will lie between minus infinity to infinity only, right? Whatever is the value. Okay, and this comes up as, how do we write it? This is equal to probability of x less than or equal to a. Okay, so similarly, what will be the discrete case? Discrete case, countable case. What will be the f of x of a for single value? Here you see whether it was x comma y. This is only for single variable. Given that we have and y less than infinity is equal to summation. So from the joint one, xi less than or equal to a, and this will be, what will be the value for y? So y of j belongs to R, the complete real number. This means minus infinity to infinity. So this is a short form of that. It belongs to R, the complete real number range. And same thing, x is equal to xi, comma, y is equal to yj. This is your discrete case. I hope this is clear. Next one, continuous case. So these are all symbols or notations, symbols, okay? So that you get familiar with these notations. And maths is nothing but symbols, right? So get comfortable. So this is, while I'm writing it, I'm telling also in the English interpretation of that too. So what will be the capital F is always CDF, okay? This capital F is CDF, again f of x is CDF. What will be the value? Similar thing, x less than or equal to a, comma, y less than infinity. This is equal to a will, x will range from here and y will be the complete range, minus infinity to infinity, and then we will have the joint PDF and we'll integrate it over the complete dy dx range, and this will be so equal to minus infinity to infinity f of xy x comma y, and we'll integrate it over dy, as I mentioned earlier. Note this dy, that for finding the value of x we integrate it over the other variable. You have seen it here, right? For finding the marginal probability of a, I am summing it over the other variable. Here also, for finding the variable for x, I am summing up over all the y outcomes. That's what it means. From here we have understood this clearly. So for whatever variable we want to know the marginal probability, is sum up the, or sum it up over all the possible values of the other variable. Okay, and what do we sum up? The joint probability or the joint distribution what we have. So this is your CDF of marginal probability distribution. Now let me formalize the this thing also, marginal PMF. Here I'll tell you one more thing. How do we derive it? Okay, so say my joint distribution is given by, this is for the discrete case, okay, is equal to probability of x comma y, comma is always read as and, is equal to probability of x is equal to x comma y is equal to y. This is my joint probability. Okay, so we have learned the law of total probability earlier, I hope remember, when we were doing conditional probability. So let me explain you again with the help of that. So we have the joint probability. So how did we do that in case of two variables? So here, for example, all the possible values. So let me draw the. So this is an intuitive understanding. So this is my sample space. This is my omega sample space. Okay, and say these are my possible values of this is my y1, y2, y3, so on till yn. So these are all my possible values of y. Okay, and then we have our this is the joint distribution. This is my joint distribution. So remember, the complete sample space is divided by all the possible values of y. Okay, the complete sample space is divided into multiple, okay, mutually exclusive partitions by all the possible values of y, and this is my joint probability distribution. So if I find the intersection of this with all the possible values of y, this will give me the total probability of the other variable. So if I do the intersection of the joint distribution with respect to the other variable or the summation over other variable, so I'll get the joint distribution, the marginal distribution for finding the marginal distribution of x. We'll have to do this. And what are the from the law of this is from law of total probability. So just divide this. Probably I'll put the link of that video also in this, just to explain you law of total probability again. Okay, so what are the probabilities? What are the properties of this? That y is equal to y1 intersection y is equal to y2. These are mutually exclusive, so this will be equal to a phi null set, and the sum of all this should cover the sample space. So y1 union y2 union till yn should be my omega. So these are the two conditions that it should satisfy, and this is my joint probability. And if I sum this joint distribution probability across all the possible values of y, I'll get the marginal distribution of x. Let me write it down as a note. So marginal probability, so here x is equal to summing up the joint distribution across all the possible values of other variable, in this case y. Okay, so I hope this is clear. This should be, by now it should be very amply clear what is marginal distribution. So do you want one more example here? So let me give you a practical example. So let me give you the setup, quick setup. Okay, setup. So I'll roll a die. Okay, setup is roll a die, fair die, plus flip a coin or toss a coin. So I'm doing two things. Okay, plus toss a coin. So I'm capturing this or modeling this using two random variables. This is x is roll a die. Okay, so what will be my sample space? 1, 2 till 6, and y will be toss a coin. So what will be my sample space? Heads and tails. Okay. So now if I, what will be the joint PMF? Joint PMF of both of the events happening, x comma y, will be equal to 1 by 6 into 1 by 2. So 1, 2, 3, 4, 6. Out of that, one possibility, and head or tail, one possibility will be equal to 1 by 12. This is my joint PMF. Okay. And now if I want to find the marginal PMF of x from this also, one more simple example. Marginal PMF of x. So this will be equal to Px of x, probability of x, okay, x, okay, equal to summation of y belongs to, what is the possible values, head comma tail, that is 2 values, and probability of x comma y, xy. This is equal to, what is the summation for head and tail? For head it is 1 by 12. This is the joint probability, right? This is 1 by 12. I'll sum it over all the possible values of y. So this is my combined joint probability PMF, and then for head 1 by 12 plus tail 1 by 12, this will give me 1 by 6. This is what is your, this is your probability of rolling a die. So if you are given this thing, from that I can take out what is the probability, marginal probability of just 2 variables. This is the combined joint one, and from that I can compute the single variables PMF. Okay, I hope this is amply clear now. And let me write the formula also. With this is clear. So marginal, other formula for the continuous case, quickly let me write that down. So what will be the marginal PDF like? So let me write down the formula for you so that you remember. So this we have seen the notations already. Okay, we have seen the notations already. Let me write it down for you. So single variable f of x, small f for probability distribution function. Okay, this is minus infinity to infinity, given f of x comma y. This is my joint PDF. Okay, and then integrate it over y. This is for x, integrate over sum over, so sum over the other variable. Okay, and this is your joint PDF. Simple. I hope marginal distribution is clear now. So quickly let's jump to conditional distribution now. So this is nothing but, again, we know this already. I'll just write it down formally for you. What is conditional distribution? We have seen this in the past. Conditional probability distribution. When I said only distribution means, I mean probability is implicit. So we know what is conditional, right? Measures the probability of an event occurring given that some other event has already occurred. Okay, this is what it is. That measures the probability of occurrence of an event given that another event has already occurred. This is coming from the past. You know this. Some event has already occurred, and what does it give? That some more new information has come, and on the basis of new information we should update the prior, okay, likelihood that we have, and then we get the posterior. So this provides a way to update our belief of likelihood, okay, based on new information. Okay, based on new information. So what is the old formula that we know already? Probability of A given B is equal to probability of A and B by probability of B only. So do we know these things already? What is this? This is our conditional probability. Okay, what is A and B? Combined probability. These are joint probability. And what is the probability of a single random variable? This is my marginal. So we have seen this joint and marginal already. This is conditional. So combined one is joint, individual is marginal, and A given B is conditional. So what this gives me a beautiful formula that conditional probability is implicit in all is equal to joint by marginal. Okay, this is the relation. This ties up all the things, three things together. And let's understand the joint one with the same example again. Conditional probability. So I'll formulate this. So the running example, the ball example that we had. Where is it? This one. So I'll use this. What is the conditional distribution? So I will let me move to the next page itself. This is the extra information. So now we have that. So now I'll write the question. So this is the setup, we know that already. This is our setup, we have seen this already. So let me formulate a new question, a conditional probability question. So my question here is, what is the probability of drawing a red ball in first draw, given that a blue ball is drawn in the second draw. So what was the random experiment here? What was the experiment? That a ball is randomly drawn from each bag such that both the draws are independent of each other. So there are two bags, A and B. Each one had 2 and 3 red and blue balls. Okay. And then what we have done, let A and B be discrete random variable associated with the outcome of the draw from first and second bags respectively. And now my question is, what is the probability? This is a conditional probability question. That what is the probability of drawing a red ball in the first draw, given that a blue ball is drawn in the second draw? Let's solve this. So same example, just some manipulations here. So what was this? What was the, let's redefine this. So A is the drawing first draw from the first bag. Okay, first bag, first draw, red ball. And what is B? B is for the second draw, and this is blue ball. So let's write it down as conditional probability. Probability of A given B is equal to, we know that blue ball has already been drawn. What is the probability of red ball? A given B is probability of A and B by probability of B. So let's find it out. Okay, what is the probability of A and B? What is A and B? So what is the probability of drawing a red ball, the joint probability, in the first draw and a blue ball in the second draw? This cell will give me, this cell here, this is 4 by 25. So this is my joint distribution, joint probability. This is equal to 4 by 25. That is a red ball in the first draw and a blue ball in the second draw. This cell will give me here. So this is the value 4 by 25. And now what is the second one? Probability of B. That is probability of drawing a blue ball in the second draw. So this is our probability of B cell. Probability of drawing probability of drawing a blue ball in the second draw. So here it is. So these are the values here. Let me highlight them. So probability of drawing a blue ball in the second draw is given here. This is for the red ball, this is for the blue ball. So this is 2 by 5. 2 by 5. 2 by 5. So 5 times, 2 times, so this will become 2 by 5. So the probability of drawing a red ball in first draw, given that a blue ball is drawn in the second draw, will be given from the, so let's see, just match it. It's a simple toy example, so let's match it. Probability of drawing a red ball in the first draw, that is from the first bag, given that a blue ball is drawn in the second draw. So this blue ball is drawn in the second draw, so this is gone. Okay, so this second draw is given. So what is the probability of drawing a red ball from the first draw? This is 2 by 5, and that's what we got. I hope conditional probability is clear. And remember that we have only got these values. This we are rechecking. This information was not present. We didn't have this information. We only had these joint probabilities and these individual probabilities. From this we calculated that this is 2 by 5, and we found out that yes, this is 2 by 5. This information was not available with us. Okay, this we calculated from this, all these joint probability. We started with this, right? These values, and then we got this. Okay, I hope conditional is clear. So let's formally define conditional CDF quickly. What will be the conditional CDF formula? So this is, so now mark the notation capital F, x given y, x, earlier it was comma, this is that straight line, x given y is equal to probability of x less than or equal to x given y is equal to y. So here it is y is fixed, and now probability of all the values of x less than or equal to x. So this is the accumulation is happening on the x variable only, and y is fixed, and this is y has happened. Now what is the probability of getting all the possible values of x less than or equal to x? So this is what conditional CDF will give you. Okay, so discrete case. So I understand this is repetitive, but this will give you a very strong repetition, will give you all the formulas feel. Okay, what formulae? Okay, what is the discrete case? Fx again given y, single line is xy. The notations, be very careful when this comma is and this is given. Okay, these notations you will keep on finding everywhere. So this is probability of x less than or equal to x given y is equal to y, y is fixed. This is equal to summation xi less than or equal to x, only one summation, x is equal to xi given y is equal to y. So this is y. So all the possible values of x given y is fixed at y. That has happened. The universe has changed, and this is my limited set now. Similarly for continuous case, so we have new information, and in the light of the new information we have to update our new probability. Okay, so this will give me minus infinity to x. Same thing, f of, this is my PDF, x given y, this is x comma y, and this integrated over dx. Okay, is equal to, I'll write it, I'll expand it a bit, minus infinity to x, f of x given y. Okay, no, so let's expand it and put the conditional value. So I'm expanding it now, right? So f of x comma y by f of y dx. So remember this comma, this is and this is given. Okay, let me correct this notation also. This will be x given y. Okay, and then always remember whenever the conditional probability is there, right? So there is one for mathematical this thing, right? So this should not be 0 whenever you are dividing something by 0, right? So this will be across probabilities that is such that probability of b is greater than 0. So everywhere you have to put that. Remember this condition, that such that probability of f of y is greater than 0. Okay, I hope the formulae are clear and the symbols. This is given, this is and. Wherever you see comma, so be very consistent. Understand this is comma, this is comma, this is given. Continuous case. This is done. Now conditional PMF. So conditional CDF is done. Now let's move to conditional PMF. So I'll always cover all the cases. Okay. So CDF is common to both. This concept is common to both PMF and CDF for the discrete, and then I'll give you the concrete for conditional. This is for discrete case. The conditional PMF would be probability of x is equal to x at a particular point. Now this is not less than equal to. Here you see this is less than equal to. This is cumulative. Okay, and here this is at a particular point. This is equal to probability of x equal to x, comma y equal to y by probability of y is equal to y. So again I'll write it. This is your comma is and this is given. Okay, the symbols notations will change. Okay, given probability of y is equal to y is greater than 0, and then similarly conditional PDF will be, what is the value? F of x given y is equal to f of x comma y by f of y of y. Okay, such that f of y is greater than 0. Okay, so there are a lot of applications. You must be thinking, why am I learning so many formulas? So this will make you comfortable with the notations. First of all, you will see all these symbols everywhere, so that will make you comfortable. Apart from that, there are a lot of applications of conditional conditional probability distributions in machine learning. Later on, when we learn generative models such as GANs or variational autoencoders, so there you will see this conditional distribution in play. For example, GANs learn the conditional distribution of the pixels of an image. Okay, what are the pixels for a given style? So what are the combination of pixels for a given style of the input image? So the condition is, what is the style in the input image? Given that, what is the probability of the pixels? So GANs of these generative models, right? The GAN that learns it. Similarly, variational autoencoders also. So this is why these concepts are very important and fundamental. Okay, I hope that's clear. Now let's move to the next topic. Within conditional. So conditional, now we'll discuss about conditional expectation. I told you, right? So we'll have conditional expectation also and variance. So we'll just extend it. So what is conditional expectation? So we write the conditional expectation of, we know expectation of x is expectation of x. Conditional expectation is again that something has happened, and then conditional expectation of x given the other random variable y has happened. That given that y has happened, the value for that is y. So what will be the example? For example, we have the conditional expectation of person's weight. So we'll have the conditional expectation of a person's weight given its height. So if you have given height, so for example, if the height of the person is equal to 170 centimeter, then what will be its weight? So this information is available. So this won't be the average weight, right? If I ask you the expectation of the weight, then you will give me the average weight of all the sample, whatever you have. Okay, but if I have given you the more information that, okay, the height of the person is 170 centimeter. So now this is the condition. Your universe has changed, the world has changed. It is limited to 170 centimeter people. So the output for this would be the expected value for, what will be the expected value? This will be the average of all the weights of all the people whose height is 170 centimeter. That average will give me the weight for the expected value for the weight of a person whose height is 170 centimeter. Okay, so this is my question. So this will give me, conditional probability will give me the height. I hope this is clear. How do we denote it? So expectation of x given y is equal to y. This is equal to summation of all x over all x. This was earlier x into probability of x comma y. Sorry, not comma, x given y, and this is x given y. The other way to write this would be summation over x of probability of x equal to x given y is equal to y. Okay, this is for all the, so this can be written better as xi. This will be xi. This is more readable. This is for all the values of xi, summation x into. Okay, this is your discrete case, so I'll write it. So this is for your discrete case. What will be the for the continuous case? Similarly, what will be the expected value of x given y is equal to y? This will be equal to minus infinity to infinity, all the possible values, x into f of x given y dx, because we are finding the expected value of x, so we'll integrate it over all the possible values of x. So this will give me the expected value of x conditional expectation, given that y has already happened. This is not changing, so anyway this will not integrate, so y is constant here. So this is for x, just to remember. Okay, so this a conditional expectation, where will we read? So this we will use when we will be reading expectation maximization algorithm later. So when this is called EM algorithm, so when we are reading an EM expectation maximizing algorithm, that time we will use this concept of conditional expectation. Similarly, let's understand conditional variance. So this is nothing but an extension. Okay, so after the arrival of new information, you update your probability. What is the conditional variance? Conditional variance would be similarly, let me write it. Let me write the formula itself. You know what is variance, I will not go through that. Variation of x given y has already happened, it has the value y equal to y. This is equal to summation over x. Okay, and then let me be very careful, x minus expectation of x given y is equal to y. So the distance of all the points from the mean or the average value, this square, given y has already happened. So how do we read it? So this is your distance, this is your expected value, conditional expected value. So this is your mean, conditional mean, and these are all the points over which I am summing up. So distance from the mean, and this square is the square of the distance from the mean, given y equal to y, that y has already happened. So this is how you read it. So there is one more formula that we derived in the last class. This is equal to expectation, and write it in the form of expectation. Expectation of x square given y is equal to y minus expectation of x given y is equal to y whole square. This is your variance. Okay, this is just for completion, you should know this. Okay, so what is so when will the variance change? So you want to find the conditional variance, right? And you are saying that you want to find the expected value of the variance. So when will the variance change? For example, I'll give you a very common example. So when you are driving a car, right? So the variance of the car's mileage, when you are driving it within the city, the variance of that value will be different from the variance of the car's mileage when you are driving it within the city plus on the highway. So there the variance will change. So one is within the city only, and and the other sample is other cases where you are driving within city plus on the highway. So the variance of the range of the mileage will be more in the city plus highway case, right? On the highway the mileage is more. So that's what will give you the variation in variance, and then because of the variation we try to find out what is the expected value of my variance and the conditional variance. Okay, so this is what is your application of conditional variance. Okay, what is the when the conditions are changing, the variance changes, and depending upon the condition, my variance is changing. And why do we need to study this? So there is one term we will discuss, that is called, whatever I have told you in the example, right? So that there is a term that captures, that is called heteroskedasticity. Okay, I always, okay, this is called heteroskedasticity. Skedasticity. So this is the, okay, this is the measure of changing variance. So when we will learn about linear regression, there I will measure this is the assumption. Okay, this is one of the assumptions. So this is the changing variance. So a model, okay, so why is it important to understand expected value of, or conditional value of, conditional expectation of variance, right? So there this will make sense when we will discuss heteroskedasticity, that is changing variance. So generally the models assume that the variance is constant. Okay, and if, okay, when we are modeling this, so if the model that captures, okay, that captures this heteroskedasticity, right? This is very difficult to pronounce for me. Heteroskedasticity. So that will give me more accurate results because it is changing some more change. Okay, that is capturing some more change in my input data that we have. So model, I'll write it. Let me write it down. Models that account for changing variance, or this word heteroskedasticity, okay, tend to be more accurate. So this is one use case, as I mentioned, right? Why are we studying this? So I mentioned, why are we studying everything? So this will be applicable when we will learn linear regression, and this is one of the assumptions of that. Okay, so that's all for this video. Okay, let me do a quick summary of all this. Okay, so let's summarize what all we have studied. We have studied a lot of things in this video, so let's go from the top. So the explanation was big, but we have covered very few things, but I hope everything is clear. So quickly summarize. So we discussed about, first started with joint distribution. So what is joint distribution? This describes the probability of two or more random variables occurring simultaneously or together. When you want to capture that, how two random variables will function, or what will be the output when they both occur together. So that's what is our joint distribution. That's what it captures. Okay, and then we understood it using an example. This was a running example where we had two bags with 2 red balls and 3 red balls, and the second bag had 2 blue balls and 3 red balls. And then we captured the joint probability distribution for each combination. So there can be like, first draw can have a red ball, and the first draw can have, so A and B, A represents the draw from the first bag, and B represents the draw from the second bag. So the first bag can have red ball, second bag can have red ball, and so on, all the 4 combinations. And this combined first red and second red. So this probability we calculate this 625, and similarly we calculated for all the 4 combinations, and this gave us the joint distribution for all the possible combinations. So we understood what is joint distribution. Then we saw the formula for all the CDF, cumulative distribution function, discrete case, continuous case, for all of them. Then the PMF, what is the formula for that? This is just a formulation. Then the PDF. Okay, then next we move to marginal distribution. So marginal distribution is that, given the joint distribution, if you want to compute the distribution of one random variable, so there are 2 or more than 2 random variables, and we have the joint distribution. If that is given, how do we compute the probability of just a single random variable? So this is what is marginal distribution. And how did we compute that? There what we did, that if we have to compute, say for example there are 2 random variables x and y, then what did we do? We kept the other value as constant. And how did we do that? So we captured all the possible values of the other variable, so that the probability of that complete range becomes 1. So whatever remains out of the joint probability is the probability that is coming from the first random variable only. So that's how we found out what is the marginal or the individual probability of that one variable from the joint probability distribution. So that is my marginal probability. Then we moved, when we saw it using an example and we did all the discrete and continuous case, then we moved to conditional distribution, which measures the probability of occurrence of an event given that another event has already occurred. And we know this formula already. And from this we formulated that conditional probability is equal to joint probability by marginal, because joint is the combination and of two probabilities, and then marginal is the individual probability. And remember that the denominator should not be 0. This should always be greater than 0, because division by 0 is undefined. Then we saw, okay, we understood using the same example. We used the same running example to understand conditional probability also. Okay, and then we found out that, okay, yes, the conditional probability is matching whatever we calculated using this. So this was conditional probability. Then we extended that. We saw the formula also. Remember this notation. So this is very thing. So these are the important notation. This symbol is for given, and wherever we use comma, that is for and. So these are important symbols that you should remember from here. When you read the papers, you should get this. Okay. Then we saw conditional PMF, conditional PDF. We did PMF, PDF, discrete and continuous case for all the three. Then we did something more, that is conditional expectation. That we know what is the expectation of a value, that is the average value. But what is the conditional expectation given that another variable, if there are two random variables now, right? So whatever this complete class is about, two or more than two random variables. So what is the expected value when another random variable has taken a value already, given that that has already happened? For example, if I have a sample or a range of values in a data which gives me the height and weight of all, so I ask you what is the expected value of the weight of a person whose height is 170 centimeter. So this expected value will give me the average weight of the complete sample. But now I have reduced the sample size by giving the condition that only for the people whose height is 170. So what did we do? That we computed took the weight of all the people whose height is 170 centimeter. That's the condition, and took the average of that, and that gave me the expected value of the weight of a person given that the person's height is 170 centimeter. I hope this is clear. And then we saw the application of these also, that we will, when we do EM algorithm, okay, so when we do EM algorithm, that time conditional expectation will be used. And there are many more cases, but I'm giving you a common thing. That's when we will apply this learnings. And then we read about conditional variance. Conditional variance is again given two variables. So the expected value of the distance from the center, given that y has already happened from the mean, from the central tendency, and the central tendency also we computed using the conditional variable. So given that, we have computed the square of the distance from the mean, and that gave me the expectation of conditional, that gave me the conditional variance. And this is computed. We saw the formula for that, and then we discussed about heteroscedasticity, which is changing variance. Okay, and then we saw when we will use this during linear regression. That's the application. Okay, thanks for watching this video. This was a long session. I hope all these terms etc. are clear. So that's why I spent this time making it very clear, very important concepts. So thanks again for watching this video. That's all for now. Okay, have a great day. Okay, see you soon. Bye for now.